Hi, today we'll be solving an intercept question using moon as a celestial body. So the intercept method is also known as the Mark-Saint-Hilaire method, and this method is used in the area of celestial navigation to calculate an intercept and bearing of a celestial body. Alright, so I have previously made videos on this method using the sun and the star and the planets as celestial body. Today's video focuses on the moon. I will provide you with the links on the previous videos in this topic along with this video below. Alright, so I'll start with the question here. The question says it's 25th of February 1992 and it's AM at ship. That means that it's morning on the ship, and in the DR position, which is the dead reckoning position or estimated position, is 20 degrees 4 minutes south and 90 degrees 4 minutes west. The sextant altitude of the moon's upper limb or UL was 5226.8 at a chronometer time of 2 hours 56 minutes and 17 seconds with a chronometer error of 4 minutes and 01 seconds fast. If the height of I was 19 meters and index error was 0.6 of the arc, you have to calculate the direction of the position line and a position through which it passes. All right, so sorry about that. So if I start with the solution, and before I start with the solution, we have to solve something called the ambiguity of the chronometer time. And I have solved this ambiguity a number of times in my previous videos, but still I'll take you guys through this. If you think that I rushed through it, please watch my other videos, and also there's a separate video titled Ambiguity of Chronometer Time. You can watch that as well. Alright, so anyhow, I'll quickly take you through this as I have with my other videos. So whenever a chronometer time is given to you, you can have two scenarios with it. So all you have to do is whatever time is given to you, just add 12 hours and write down another scenario, because when the chronometer shows 2 hours 56 minutes 17 seconds, it could be 2 in the morning or 2 in the afternoon, which is 1400 hours. And because the chronometer looks like an analog watch, and on your ship you don't know what exactly is the time at the GMT. The chronometer actually is a device on the bridge which gives you the GMT time. So when you look at the GMT time, you could be on a very different longitude based on the GMT, and so you don't know what exactly is the GMT time. Is it 2 in the morning or 2 in the afternoon in comparison to your position at the ship? Alright, so in your position, depending on your position or your longitude, it could be morning on your ship, it could be night at the GMT, or vice versa. So we have to figure out from the chronometer time. So anyhow, whatever the chronometer time is given to you, just add 12 hours to it and then write down both the scenarios and then apply your chronometer error. The same error is applied in both cases. Because the error is fast, that means chronometer is running ahead of GMT. We will subtract the error in both the cases. Then you get two scenarios of the GMT time, and to figure out which is the correct scenario, you have to apply something called the zone correction. Now the zone correction is obtained from the longitude in time, or LIT. LIT stands for longitude in time. That means every ship should have its own time based on its own longitude, which is not the practical way of timekeeping, and that is why we use a correction called zone, which is the more practical way of timekeeping. A zone refers to a range of longitude. If your ship is within that range, that is the time it should be keeping, so that all the ships have the same time, and it helps to do business in world and to do business with the ports as well. Alright, so anyhow, you can calculate longitude in time or LIT by dividing the longitude by 15. In this case, it's 90 degrees 4 minutes divided by 15, which gives you 0600 16 seconds. So 06 hours 00 minutes 16 seconds. This is the LIT. Now LIT is always written in hours, minutes and seconds, and it can be not a round figure, but for zone it has to be a round figure. It has to be a whole number. So since the LIT is closer to 6, we will make the zone 6, and that's why you have the zone 6 here. And you see a negative sign. The negative sign is because you are in west longitude. Whenever you are in west longitude, you will subtract your zone from the GMT, because GMT is ahead of you. Alright, so imagine yourself being in America, which is in west longitude, and GMT is the time at UK. The time at UK will always be ahead of you. Alright, and similarly, if you are in east longitude, say for example you are in Australia, or you're in India, or you're in any of the Asian or Middle East subcontinent, then of course you are ahead of GMT because the time at UK is behind you. All right. So whenever it's west longitude, just subtract the zone. Alright, so in case you are wondering in the first case, how did I subtract 6 hours from 2 hours? Well, just add 24 to this and make it a bigger number and then subtract it. Alright, and then you get your zone time. Your zone time is the time kept on your ship, also sometimes called ship's mean time or SMT. In the next case also, just subtract 6 hours. So in one case, you get 20 hours, 52 minutes, 16 seconds, and in the other case, you get 8 hours, 52 minutes, 16 seconds of zone time. Alright, so how do I know which is the correct zone time and resulting GMT? Well, the hint in the question is that it's morning on my ship and it's 25th of February morning on my ship. Out of the two zone times, I see only one time which says it's morning on my ship, which is the second case. So I will write 25th here, and I know this is my case, so I will cancel out the first case. I don't need this one. Now I have to figure out if the date at the GMT is also same after subtracting 6 hours. Well, yes, common sense says it is. So the date at the GMT is still 25th, although they are about 6 hours ahead of the time on my ship. Alright, that is why your correct GMT time is 25th of February, 14 hours, 52 minutes and 16 seconds. Make sure you work with the correct GMT time and not the zone time, because you have to use a GMT time to go into your Nautical Almanac and get the values from there. Alright, so we'll go into the 1992 Nautical Almanac very soon, and I will find out the GHA for 1400 hours first for 25th of February. Then I will go into the increments pages. Increments are always added. Increment will be found for 52 minutes and 16 seconds. Then I will find the V value also from the Nautical Almanac, and then go into the increments page and find the V correction. Alright, so I will not go too deep into it, otherwise you guys will get confused. So let's go into the increment or rather go into the Nautical Almanac for 1992 and find out a few of these values. Alright, at the same time I'll also show you where I can get my declination value from, this value here, and my D value as well. Alright, so these are some of the values I can get from the same page. So instead of going to and fro, back and forth, it's better that I go into one time and then show everything to you. Alright, so let's go into Nautical Almanac. 25th February is the date. So I've kept this page ready for you guys. So if I can show you here, this is 25th of February is here, 1992. So this is 25th of February. I can zoom in a little bit so that I can show you both the, that's right, if I zoom, okay, I think this is good enough for me. The time and the hour should be, and moon should be able to see. So 14 hours, just go horizontal from here. So you can see you have to go further. This is sun, right? So you can see this is moon here on your extreme right hand side. Alright, and if I erase this, then I'll circle it again. So this is moon, this is moon, and then you can see the GHA values are given under this column, the V value is given under this column, the declination is under this column, and the D value is under this column. We'll also use the HP value, which is the horizontal parallax, but I'll come to that later on. Alright, so for 14 hours, just find out what is the GHA is, I think 117, then this is the V value, this is the declination value of 24 degrees 16.3 south, and then this is the D value, and I'll come to the horizontal parallax of 55.4 later on again when I'm resolving the sextant altitude. Alright, so just note these values down. The reason I show you these values at one go is because it's easier for you also and easier for us, so not to go back and forth. I'll go into the increments page later on because I want you just make a note of these values, and then I'll go back into the solution and show that these are the same values I've been using. Alright, so again I have shown you the GHA value, I have shown you the V value, I have shown you the declination value and the D value. Now I will show you where to get the V correction from and D correction from. Alright, so the D correction is this value here. D correction is added. So if you note that the declination was increasing going from 14 hours to 15 hours. So from 14 hours to 15 hours declination was increasing. So you will add the D correction. Alright, but the V correction is added based on the sign of the V value. So let's go back into the Nautical Almanac and go into the increments page for 52 minutes and 16 seconds, and for a V value of 9.7 and D value of 2.3, and then increment also we'll find out. All right, so 52 minutes and 16 seconds. There you go. So I have the page opened, but I'll erase some of this stuff for you so that you guys don't get confused. So 9.7 and 2.3 was here as well. So you can see the V and D values you get from these columns here. So for 2.3 of D correction, you get this correction of 2, and 9.7 of V value, you get this V correction here, 8.5, right? And the increments is, of course, moon is this column here. So for 52 minutes and 16 seconds is on the vertical column, 16 seconds is here. This is your increment, 12 degrees 28.3 minutes. All right, so at this point of time you can just pause this video and just have a look at this page and see where I got these values from. Only when you're satisfied you can go back, but I'll keep going, otherwise the video becomes a bit long, and I've been asked to keep the videos short. So I'll keep going, but you pause wherever you think we are rushing through or you didn't get the idea. So I've kept this page for some time now, but I'll go back and into the 25th of February now. All right, so 25th of February is this page here, and if I can show you about the declination, you can see the declination is increasing from 16.3 to 18.6 going into the next hour, right? That's why the D correction will be added. So I'll erase this and you can see, right? And also let me show you the horizontal parallax now, because otherwise we'll have to come back to this page. So the horizontal parallax is here, 55.4. So from 12 hours all the way to about 15 to 16 hours, it will be 55.4. So remember this value of horizontal parallax when I use it later on. All right, so I don't have to come back to this Nautical Almanac. Anyhow, so I showed you where to get the increments from, and the V correction and the D correction as well, right? So let's resolve the GHA first. So I've resolved the GHA, I've added the corrections, I've got the GHA, and then I've got my longitude of 0904 minutes, and longitude west GHA is the best. That means GHA will be more than LHA. So you will subtract the west longitude. So longitude west, this is a rule of thumb, longitude west GHA is the best, all right, compared to LHA. So GHA has to be more than LHA. So whenever you see west longitude, just subtract it from the GHA, and that gives you the LHA. Now you can name this LHA and you can name it west, because if LHA is between 0 to 180, it's west, and if it is more than 180 to 360 degrees, it is named east. All right, so make a note of this rule of thumbs. It will help you understand how to name things when we go further into the question. All right, so we've got the declination as well. I've applied the correction and I've got the final declination as 2418.3 south. I've written down the DR lat as well, because I'll be using this for reference later on in the question. Let's resolve the sextant altitude now. The sextant altitude is given to us in the question. The index error is off the arc. Whenever it's off the arc, you will add it. We add it into the minutes. We get the observed altitude. Then we have to find the dip correction for a height of I of 19 meters. So let's go back into the almanac, and what I'll do is I basically use these pages here at the end of the Nautical Almanac, which are called altitude correction tables. All right, these are called altitude correction tables, and these are normally towards the end of the Nautical Almanac. All right, so you can see for a height of I is here. This is dip correction is also height of I. So height of I in meters, 19 meters will be lying somewhere between here. 18.8 and 19.3 should be minus 7.7. All right, so I'll go back, and you can see that's the correction of height of I, minus 7.7. Height of I correction is always negative. All right, once you subtract it, you get an apparent altitude. All right, so this app altitude stands for apparent altitude. So you take this value of 52 degrees 19.7, and you go back into the tables from where I got my height of I from, and you can find out the main correction and the horizontal parallax correction. So remember the horizontal parallax value I showed you before, the horizontal parallax was 55.4. Well, you use this value to find a correction. All right, and then you will add these corrections. So let me show you where to get these values from. So all you have to do is remember the apparent altitude value of 52 degrees 19.7 minutes. All right, so I'll go back into the same page. So you can see I have come back into the same page here. So I'll go to the next page here. So for 52 degrees and 19.7, you can see the apparent altitude values of degrees are in the horizontal column here. This is the degrees one, and this vertical column is minutes. So for 52 degrees 19.7, this is 52 degrees, 19.7 will be somewhere very close to 20, so your mean correction will be 45.2. Also your horizontal parallax value is here for 55.4, which is very close to 55.5, and your moon's, it was moon's upper limb. Remember in the question it says it's upper limb. You go into the column here because this is where your apparent altitude column is for upper limb. So L stands for lower limb, U stands for upper limb here. So you see the U one because it's upper limb, you get a correction of 2.9. Now I take this correction, go back, and that is what I have applied, 45.2 and 2.9. Add the values, you will get the apparent altitude corrected, and then whenever it is upper limb, you apply a correction of minus 30 minutes. Alright, now this is also mentioned in the table here. So if you go back into the tables, you will see on the first page, on the first page, it says over here. Alright, it says over here that if all corrections are to be added, the 30 minutes is to be subtracted from the altitude of the upper limb. Alright, so just subtract 30 minutes and then you get your true altitude. Then subtract the true altitude from 90 degrees and you get your true zenith distance, TZX. TZX stands for true zenith distance. In some books they also write it as TZD. It's the same thing, true zenith distance. Once you get your true zenith distance, you have to calculate something called the calculated zenith distance, or CZX. CZX stands for calculated zenith distance, and you can calculate it by using the formula here on the scientific calculator. There are also other ways to do it, but we use a scientific calculator because these days everyone has a scientific calculator, right? And then you see over here it says plus and minus both. Well, this depends on whether your lat and dec are same names, then you will add it. If they are different names, you will subtract it. So in this case, your latitude and declination are both south, right? So you will add it. Simply put in the values of the LHA, the latitude and the declination. Again the latitude and declination, and you will add it because the latitude and declination are same names. They are both in the south. Then you solve the equation. You can compare the values with the one that I have written here, and then take cos onto the other side, becomes cos inverse to get the CZX. I stick to 5 decimal places because it gives me reasonable accuracy. You can go more if you want. Don't go less because the more you go, the better is the accuracy. And then you calculate this calculated zenith distance, alright, which should be very close to the true zenith distance. Then you can write down the true zenith distance here and the calculated zenith distance here. So the true zenith distance from above and the calculated zenith distance is what you have just calculated, right? Then subtract the smaller from the bigger. Alright, so in this case CZX is bigger, so you subtract TZX from CZX, you get intercept of 2 minutes. Now this difference between TZX and CZX is called intercept, and that is 2 minutes. And then I have named it towards. That means it's towards the celestial body. How have I named it towards? Well, there's a rule, if you can remember this rule. It says true if tiny, then it is towards. That means if the true zenith distance is less than the calculated zenith distance, then it is towards. Alright, if true zenith distance is more than calculated zenith distance, it is away. Alright, now in my staggered videos on staggered observations, you can see how I have applied this rule of towards and away. I will not go into all that in this video here. So if you don't know what towards and away means and how it all gets involved into actual plotting of the ship's position, please watch my video on staggered observations and you will see how it is all applied. Alright, I'll continue now that I've calculated the intercept. I need to calculate the position line. So to calculate the position line, I have to calculate the bearing. How do I calculate the bearing? Well, I can calculate the components of A by dividing tan lat by tan LHA. Simply put in the values in the equation here and write down the value. So the value you'll be getting in the calculator is 0.43. In case you get a negative sign, please ignore the negative sign. Alright, ignore the negative sign. Simply write in the value here and then you have to name it. In this case I have named it north. Why? Because it is named opposite to latitude. unless LHA is between 90 and 270. Since your LHA is not between 90 and 270, you will name it opposite to latitude. Latitude is south, so you name it north. Then you calculate component of B by dividing tan of declination by sine of LHA. Simply put in the values again. Again, if you are getting a negative sign in the calculator, ignore the negative sign. Just put in the value. You might get 0.699 something. Just make it 0.70. I stick to 2 decimal places here. You can go more if you want to. Alright, but remember to ignore the negative sign. Don't include the negative sign here. These values are always positive. And then I have named it south. Why? Because this is named same as declination. Alright, so your declination is south, you will name it south. Then write down the A and B values here. The rule is if they are different names, you will subtract it. If they were same names, you would have added it. In this case, they are different names. One is north, one is south. So you subtract it. Just subtract the smaller number from the bigger number. Don't worry what is written above. C values are always positive. They are negative. Alright. So you get 0.27 and then you get the name from the name of the larger. In this case, south was larger. So you retain the name of larger, which in this case was B, which is south. So you will name C south. Then you calculate the tan of azimuth using the formula 1 divided by C times cos of lat. C you have got from above as 0.27. Latitude you know, it's given in the question. Solve the denominator first, then divide 1 by it. Then take tan to the other side. Becomes tan inverse. Again, I've stuck to 5 decimal places. You can go more, don't go less. And you will get the azimuth of 75.7 degrees. Which for practical purposes I rounded off to the nearest number, which is 76 degrees. You can continue with 75.7, it's still correct. Some books continue with decimals, some books they round it off because sometimes bearings need to be plotted on the chart and you can't plot a bearing of 75.7. Alright, in both the cases it's right, it all depends on what your lecturer tells you to do in the exam. Then you can see I have named it south and west. Where did I get this south and west from? South comes from name of C. So if you see above, then your C is named south, right? This is where it came from. West comes from LHA. Remember, we had named the LHA before, earlier, I had named it west, there, that's where it comes from. Now, south 76 west is also equal to a true bearing of 256 degrees true. Why is that? Because if you are south here and west here, and you are going 76 degrees south, from south you are going 76 degrees towards west, this value is 76 degree. If this is 180 and this is 270, you will add 76 to 180 and this becomes 256 degrees true. Alright, once you get the bearing, simply subtract 90 from the bearing and add 90 to the bearing. You will get 166 and 346. This becomes your position line. So your PL stands for position line. Alright. So you got the position line and the position through which it passes. Alright. So I hope this was clear to you, and I hope that it was easy enough to understand. If you are wondering now what to do with these position lines and the intercept that you've calculated, how it helps to calculate the position of the ship or plot the position of the ship, please, like I said before, watch my videos on staggered observations. I have put up a number of videos on that topic and you can watch it and understand how this all comes together. If I try to include the plotting in this video, it will get longer. So thank you for watching. I'll see you soon with my next video. And again, thank you to all my lovely subscribers and people who watched my videos and give me feedback. I really appreciate all the encouragement.